infer this stuff, whatever it is we want to do. I will ask some questions about, does it matter which scale you put this on? And you should be thinking just as a reaction, it probably could. And so we probably want to be careful. And we'll talk about classical analogs to inferring this parameter as well, and what scale you put everything on. We'll ask the question of, does that scale preserve the property that you're guaranteeing up front? And the news on that is pretty bad, but for the Bayesian, I think the news is very good. We'll start motivating a concept, another reason to be a Bayesian, that doesn't just look like, so far I would say all the stuff we've done, we've kind of said like X bar is good. And we kind of saw that in both the binomial example and the normal example. X bar was really good in the normal example, and X bar was pretty good in the binomial example. Just a little bit of penalty in there. So we're going to be jumping and answering questions about inference, about this, and we'll be a little bit fictitious about our inference, and we'll say that we know the mean. Just as a prelude, you will use these conditional distributions. So when I'm locking down parameters, I call those conditional distributions. If I lock down all the parameters but the one I'm interested in, and I don't do anything with it, those are called full conditional distributions. And those are super useful when we build up our MCMC theory. So we'll be cycling through those distributions and touching them iteratively. So we can build some really neat iterative algorithms out of this stuff. So fiction will become useful. Later on, we'll see how to do joint inference on those. Not quite there, but we're about a week away from question. I do want to talk just a little bit more about this parameter. This is a location parameter. And we never quite remember exactly the terminology, but we know this has something to do with the scale of the distribution. And so whether I flip it up or down, we might call it a rate parameter or a scale parameter like in the exponential distribution. So that sort of stuff, and I don't care if you remember. We call it the scale or the rate, or we take square roots of it. What is it now? You know, I just want you to know what that parameter means. Flipping it upside down is no more complicated than thinking about it. Dylan asked a question, because you take the square root over this all the time to put the data on this, to put the parameter on the same measurement scale as your original data. You can think about it that way. Do we ever take the square root of this feed parameter? And I don't know who he is, but I never have. But it's totally reasonable to think about it. And I'll tell you one of the priors that we use, it won't make any difference in your inference how you treat it. If you end up flipping this upside down, or you look at sigma squared, or you look at sigma, or you look at square root of phi, or something like that, you call that a new parameter. One concept we might be thinking about is transformation invariance, and that's what Jeffreys priors are all about. So I will allude to what a Jeffreys prior is, but we're still a couple weeks away from working through those calculations. We're getting a lot of stuff all at once, which is kind of really cool. So later on when I say Jeffreys priors, I'll say we've already been touching them. We've been using them. The beta half-half happens to be one of them. And so some good news is that all the Jeffreys priors for one-dimensional analysis are limits of the conjugate properties. And there's a proof out there that you take an advanced base class, they march you through that proof. That's kind of cool. So all this conjugate stuff that feels like it's really convenient for us, it actually has some theoretical background, or theoretical underpinnings, I would say, that says it's the best stuff to use, but you have to pick which member of the conjugate family you want to use. And in some cases, they might be improper distributions. So just remember, for this location parameter, so what that's doing is it's just basically shifting where this distribution is. So I'm thinking of this as a function of x. I'll call this f of x, given mu in sigma squared right here. So it's a normal distribution. And this parameter right here, if I move it to the right 5 units, this whole distribution moves to the right 5 units. So if I move it to the left, delta units, the whole distribution shifts to the left delta unit. So it's really easy to interpret this, that this is fixing the location, and it's on a linear scale. So it's really just telling us what the linear shift of that distribution is, i.e. its location. So again, if I shift it by 5 units, the distribution shifts by 5 units. This parameter is not like this. So if I move this 5 units, it doesn't like slide the distribution 5 units in any linear way. It's on some other scale. But this one's really easy to interpret. And I would say that's one of the things that people think is natural. So when I ask people about means and stuff like that, I hear this word natural all the time. I'm like, what does that mean? It's not what nature is. It's that stuff out here. You know, it's not mu and normal distribution. But okay, we've got language for everything. I get it. It feels intuitive to us. So I understood what the mean was when I was in 7th grade. My understanding hasn't greatly evolved since then. So it's that thing. It's easy to understand. What we might want, so I'll just write this down as a goal, we might want a prior that doesn't supply information about the location. So this might be a goal right here. And this has a name. I can describe that mathematically. And this is called location invariance. Meaning that if I take the distribution, my prior distribution, and I slide it around from the left to the right, I want to make sure that that doesn't perturb my posterior. So what I mean is I'm going to change something, I'm going to vary something, i.e. the location of my prior distribution, but the location of my posterior won't move. So that's what invariance means. I move something and something else doesn't change. So I've got a knob, I can wiggle it, and it has no effect on something. So that's the word invariance. And it doesn't mean anything on its own. If somebody just says, oh, it's invariant, you have to tell me what it is you wiggle and what it is that you're preserving. And so the way we say that in shorthand is location invariance. So I move the location of my prior and the location of my posterior doesn't move. So that's kind of a weird thing to think about. I can wiggle something as extreme around as the location. Now I'm not saying mean, because I can't think of a distribution with a mean that I can do that to. If I tug on the mean of the distribution, it's going to pull the location of the posterior. So I have to be thinking about a weird distribution that I'm sliding its location around, and I'm not mucking around with a mean. And that seems impossible. And the reason that seems impossible is because it is.
Would that be like some sort of inverse graph delta kind of thing? Like where it's...
You take the point mass and turn it sideways? Yeah, sure. Yeah, I could think of it that way. It looks like this. There's only one function I can think of that does that, and that's this function. If I'm drawing a perfectly straight line that goes off to negative infinity, this is the concept, off to infinity. If you don't like that, you can anchor down these points and build in actual boundaries and just think about it as you pull those to the left and to the right. So, and what that would do. So, if I had something that was actually finite, bless you, if I had something finite and it was truncated here, I'd be thinking of this as a uniform distribution. Now, the posterior, if the likelihood that I was talking about looked like this, right here, in this number, I'm going to say this number right here is like -3, and this is like 3, just to give you scale. And this number right over here, this is like -1 million. And this is +1 million. So if you don't like my line or something like that, let's draw some dots in there so you get the idea. This is way down here. if I ended up taking this uniform distribution that I'm building, it would be super thin right here, because it's way up here, it's got this 2 million width, so it's 1/2 million is the height of this thing. That basically, if I yanked on this, it would really only change the resulting posterior a little bit in the tail, way over here. And that tail is coming down so far, I can barely see it, but it's over here. And so, if I slid this distribution around a little bit, it would move those tails just a little bit. But it wouldn't like change the action in the bulk of the posterior. And so, if you like thinking about that, hey, I can make this even wider. Why stop at 1 million? I'm going to make this 1 trillion, gazillion, bazillion numbers I don't even know. Big numbers. So, biggest numbers you can think of. I could do that. And eventually I would limit to something. Mathematicians like to think about that in terms of abstraction. They do themselves a real disservice when they start asking things like, is infinity real? Well, it's not. It just isn't. It's a concept. There's nothing in the universe that is infinite, in my opinion, my humble opinion on this. I see this all the time. The time isn't. It's finite. It's on a lattice. Everything looks like a lattice. So saying that, I could be wrong, and maybe this infinity thing is actually real, but I don't get myself bent into a pretzel about it. I used to. So I used to think all the time about it, and I used to think about it when I was a child. And I looked up into space, and I go, where does it all go? And all that stuff, you can do this forever. Nobody's ever given me anything satisfactory except for, it's probably not the way it works, reality. But it's a very nice mathematical concept, so wherever you are philosophically on all of this, a limit is a concept. Maybe it's a real thing, but at the end of the day, we get an answer with this. So I got this distribution, and the way Bayesians usually like to think about it is this is going off for infinity, and it's got no real height to it. So that's not a distribution. You can't integrate it with that. But we still like the concept, and we like the limit. If you don't like the limit of that, you can use a different uniform, or you could use a different normal with the variance flattening out. They're flattening out the same thing. So in terms of thinking about this conceptually, you might want to think of this as a uniform, or you might want to think of this as something like a normal centered somewhere. I'll call it mu naught, with infinite variance. Now, of course, nobody likes when you write things like this. I don't even like it when you do that. So I'm thinking about, are you describing a process to me, or are you telling me I code something up? Like, what am I thinking about there? But if you want it to be a little bit more, like I don't really mean it, this is a concept, I'd be doing something like that. And that would be looking flat. Flat as this thing is getting bigger. So again, it's not an actual distribution. So I used to think very deeply about this, and I got not really anywhere that I'm like, is this actually Bayes' theorem? Is this what Bayes' theorem says? I thought they had to be probability distributions. And I guess I can kind of like tuck it under the rug by thinking about the resulting posterior with a finite prior that's proper, some normal, and I can think about what it limits to in the posterior, so I'm not really thinking about the prior at all. And for some reason, that's an easier thing for me to digest, because I know what the goal is. And I'm not ever having to think about what does the prior actually mean. So, saying that, you're welcome to think about this distribution any way you want. The point being, a flat distribution, if it is all the way from infinity to negative infinity, is I slide that distribution around to the left and the right, employing this concept of infiniteness, I can't tell that I've changed the function. It's the same function. So function I can slide from the left to the right, any units on any scale, and I can't tell you've changed it. There's only one function in the world that looks like that. And this is this perfectly flat function. I think we can all conceptualize that. So that's called location invariance. I'll say there's another concept called scale invariance, and we're going to touch that in a little bit. So scale invariance. and location together. Both of these together are called hard invariants. So you might be thinking, what does it mean to be scale invariant? Again, there's a sort of naturalness to the flat distribution. And the way we write that down, we usually do this. So this is the notation we use to describe this. And if you think too hard about that distribution, what does it mean? You'll keep going circular and go, it's not a distribution. What does that mean? Again, we're thinking about it as the limit, this thing that we would have done. And it doesn't matter which order we do it. We could have multiplied by the flat prior and came out with this posterior, or I could have taken a conjugate prior, taken the limit of the variance, and I would converge to the exact same. So from an engineering perspective, I just think of this as multiplying by 1. I've done this flat function, and the concept is the thing. Okay. Anybody know what scale invariance means? So if I wanted to do something like this, what would be the scale invariant prior? I bet if I were in 7th grade and you moved your hands in just the right way and slid them back and forth, I would have gone, beautiful, you know, and come up with this. I think that I was at the intellectual level to know what location invariance meant. You can tell me what infinity meant, and I could have just said some huge number you can't even think of it, and any number that you can think of is bigger than that. Good enough. I became a math major when I started. I don't understand this stuff. Anybody have any idea what a scale invariant prior would be? One over sigma. This would be true if it were this. So if it were this, it would be that. So you're very close. So I'll tell you a little bit more. So just this right here, sigma, this would be 1 over sigma here. So if you like to not think of that as an operator, you can call that variance. So I'm not squaring something. So notice that these both have kind of the same asymptotic properties, even though they're different parameters. That this is a divergent series right here. So if I try to integrate over that thing right there, the tail doesn't come down fast enough for it to stop adding to something, and this will explode. So I'll just write this down. So that could be this one. It could have been this one too. They're the same functions over whatever their arguments are. So they have the same sort of behavior. It looks like this, and this tail's pretty fat, and it keeps adding. So when you learn this in calculus at some point, and if you integrate over functions like that, you get the logarithm of that. And so if you try to stick infinity into the logarithm, it explodes on you. So that's the part of the calculation where you go, that's what a divergent series is. And then your grad TA says, no, that's no proof whatsoever. Do the sandwich deal. Take the limits appropriate. Not just show that when you plug infinity in, you don't get an equation that works. They both have it. I don't care how you think of it. So, anyway, this is an improper prior as well, is what I want to point out. And keep in mind the range of this parameter is 0 to infinity. So we don't want to stack mass in any one place. We want to be diffused in some sense. And in terms of scale parameters, this in some way is objective, and we have to talk about what that actually means. But these are scale invariant, and I'll try to explain that to you either by the end of this lecture or the beginning of the next one. I tried to do it just by talking about scales and multiplying and how multiplication works. People do not understand how multiplication works. And the way to check is ask them what a logarithm is. And if they don't know that, then they don't realize like exponentiation is like multiplication, you know, that sort of thing. So what logarithms are is going backwards. And I find that even really smart people get kind of mentally tied by that. So talking about scale invariance can be really tricky, but I think I've got a lecture for you guys this time where I can unravel this. We'll see how I do. Let's do some inference. Let's do this problem. So same problem, xi's, normally distributed, mean mu, variance, sigma squared. And I'll just keep reminding us I can arbitrarily think of the inverse of that. We do want to be thinking about whether or not it makes a difference. And it can. So I'll just say this, just real quickly from classical stats, just as a review. So all this stuff is kind of aside from our Bayesian understanding of this problem, but it's good to have some anchor points. So if I were going to estimate this, I want an estimator for sigma squared. Actually, we denote that by throwing a hat on top. So estimator for sigma squared. Who's got one? And I'd be shocked if nobody has an estimator. So some professor, they're right about to get their Nobel Prize, and they're like, please help me real quick. I need to compute a standard deviation real quick. Let people know how close I am to the truth. I'm pretty sure it's pretty close because I'm a good scientist. I keep getting the same answers. But I need to seem like I'm more mathematical, more objective. So somebody yell me out.
1 over n minus 1.
1 over n minus 1.
Summation of xi minus x bar squared. Xi minus x bar squared.
That is an estimator, that's true. This one is usually referred to as S squared. Seems like every textbook, a lot of times we don't agree with each other on notations. This one seems to be persistent across countries. S squared is in the book in China. So a lot of times we don't agree with each other, but for some reason this one caught on. This is an unbiased estimator, maybe. Depends on what you get to know. Keep in mind, in this problem, and I appreciate Michael's answer, this is known. So this is an unbiased estimator of everything if I just have the xi's, but I didn't use where it was centered, and Michael decided to estimate that for x bar. It's fine. If n is relatively big, he's going to converge real quickly. He knows all kinds of stuff about x bar. So he's not too worried about it. Can anybody give me a better estimator? Just by a whisker. It depends on what n is, but if n is really 4, would I really want to do this? Probably. Better estimator. So I'll call it sigma hat squared 1. Actually, let's just give us a couple of these. Okay. This is what I do. If we did a simulation study and we were looking at MSE, mean squared error, to measure how close we were to the truth, and Michael and I bet a bunch of money on who was close on average, Michael would win every once in a while, but not often. So he would get lucky. So there'd just be some weird little doubt thinking he came around and would budge that little thing in some lucky direction, you know? But as n got bigger and bigger, I would always be beating him. And it would be by a tiny, tiny amount. So this is better. So this is the degree of freedom of the problem, and some people have tried to explain that to you geometrically or whatnot. One way you can just explain this is expectation of s squared is equal to sigma squared. And I like this estimator better. So in terms of knowing mu, this is the unbiased estimator. So if I didn't know either one of them, and I wasn't subscribing to the fiction, I would probably have to use maybe the one that Michael saw. And we're going to see this function pop up in the Bayesian analysis eventually. Not in this first lecture, but in our second attempt at touching variance, we'll see how Bayesian uses S squared. It's similar, but a little bit different. So we're equivalent. So this is just some other estimator right here. And if you happen to divide by n minus 1 right here, no big deal, because hopefully n is big enough that it doesn't make a big difference. But anyway, people like this property. This is unbiasedness. And people get really stoked on being unbiased, even though their variance could be all over the place. I'm unbiased, but every time I give an answer to anything, it's crazy. But if you average all my answers together, there's some semblance of something reasonable. Wouldn't be helpful to any particular individual. So something about how stochastic and how much the estimator bounces around is also part of the equation. So you should be thinking about how variable these estimators are. This one is less variable. So that's pretty cool. If you want to know more about that, take a grad inference class and they'll drill down into all those things and ask you to prove them and stuff like this. This isn't too hard to prove, but there's a little bit of work to do. So in figuring out what x bar is, what the expectation of its squared is, and you can use various formulas. You learn in probability class and answer that. I'm not going to ask you to prove this, but it's always a good idea when you see these results. See if you remember it. Okay. Let me just ask this question. So similar to Dylan's question, if I ended up saying, I don't like this on the unit squared scale, so keep in mind, variance is just this. So in general, variance of a random variable is just equal to the expected value of that random variable minus its expected value all squared with that expected value. Right here. So this expected value right here is just ZFZ dz over all its range. This expected value is that quadratic thing. I'll write it out like this. Z minus expected value of Z. But that's this integral. So I'll put omega Z. This is also omega Z. Squared FZ dz. That's how all expectations work. You know, I don't even need to know or memorize a formula. I see expected value and I'm taking that function and I'm integrating it against its sampling density. So it's really just an average. So it's an average of quadratic stuff. How much things, on average, vary quadratically. And this is an estimator of that. And so they're very similar to each other. Dylan was talking about all these different ways of scaling things, and can I think about it this way? If I took the square root of the expected value of s squared, is this equal to s? No, it's not. And the reason you know is because I've taken some transformation of this thing right here. So this is bias. Which way does the bias go? Does anybody remember? Jensen's inequality. Which way does it go? It's less. It's always less. So that's not true. And if I looked at something like this, s squared right here, this would not, the expected value of this thing would not be equal to 1 over sigma squared. So it's not unbiased. When you take transformations of things, you usually break the properties that you're looking for. So if I could do one thing in my life, I could just go back in time and say, if you care about that and you want it on the same unit scale, why don't you build me an estimator of sigma that's unbiased? Oh, that would have felt so good. But I would have wasted a lot of time in class. So again, it's kind of a moot point, and the question is how close is it? But for a Bayesian, maybe our life is a little bit easier. And we can start talking about properties of our distributions in invariant fashions. Keep in mind, a Bayesian isn't just giving you the mean of the distribution. They're giving you the whole distribution. And so what I want is I want to be able to transform one distribution into the other distribution and not lose any information. So let me just show you an example of that. So going back to our scale invariant priors, I want to just do some transforming real quick and see where we're at. And if you guys don't remember how transformation of variables work, I'd be prepared to give you a full-blown lecture on that on Thursday in the review session. And if you guys all petition on Slack, we really need that on video, I could give you a video. So let's just review transforms. Just real quickly, I'm just going to write down the formula. So say I've got some distribution, I'm going to call it f of z. So f of z, it's just my density. I'm going to put down some superfluous notation right here. And I'm just going to say, hey, this is the density function of z, and I'm going to be really specific about this. That the random variable at hand is z. What else would it be? And that's why I haven't been writing it down. So it's just some function. Say we have this. And say we're not interested in z per se. So you could be thinking of z as like sigma, and we're going to use that as an actual example in a second. Say I'm interested in a function of z. And I'm going to say this is a one-to-one function, just to make our life easy. If it's not one-to-one, break that function up into all the regions of one-to-oneness. It will be unique. You can find that in different ways and do this calculation in all those subregions. And this will work. So I'm going to say that's a one-to-one function. I'm going to call this something else. I'm going to call it some other random variable. I'll call it y. So just arbitrarily. And because this is one-to-one, if I tell you y, I've told you z. And if I tell you z, I tell you y. So there's a way of mapping back and forth between these two things. So G inverse y is equal to z. So that's what an inverse function is. And if I tell you it's one-to-one, I'm telling you that function exists. So presumably I can write it down. I can definitely compute it. So here's what we end up doing. If I wanted a new density on y, right here, and this is why the notation is important, I want to transform this random variable. So what I mean when I say that is I've got some distribution. I'm going to say this is what z looks like, f of z, z. So I'm going to sample a heck of a lot of times out of this. I'm going to grab a lot of points. I'm grabbing more points in this little node, grabbing a bunch of points in here, but not as many as I grab in here. And I don't grab too many from the tails, but every once in a while I grab them. That's what sampling means. So I've got all these zi's. So in an engineering sense, all I mean when I'm transforming is I'm just taking the yi and I'm plugging it into this function. So that's what I mean to transform. And I just compute what it is. I've got this function, and from that I get a new distribution. And I'm going to say this one looks like this. Who knows what it looks like? So I can draw a histogram of all of these. For every zi, I get a yi, and I get some other histogram, and it shapes kind of like that. So they can look dramatically different from each other. So if I knew calculus, I could compute this function. And that's what that curve is right here. And if I had a computer, I could just plug it in and get the histogram and use it for something. Personally, computing power aside, I like the computing answer just perfectly fine. But if I have to do this whole sub-calculation, it can bog down other calculations. So it's good to know that. What you do is you take fz, this density, and anywhere I see a z, I'm going to replace it with my new name for z, this thing. So I'm just substituting that in. I see z in this function, I plug that thing in. And it seems like the calculation would be done, and if this was a discrete example, you would be done just by doing that. But what we have to remember when we transform something is we morph the whole space. And so when we integrate over that space, area hasn't been preserved by doing this because we're putting it through some function and changing it. You can think of it as a linear function or something like that. If I have a function x, and I want to multiply that by 2 and call that y. So y is 2x, and just stretch the space by 2. So I need to account for that factor of stretching it. So I've changed what area it kind of means. And the stretch factor is this, dy. And it's an absolute value because it's morphing area. If you want a more technical derivation of this, I'm just going to go back to what probability is, tell you how to make a derivative. If you want that lecture, I'll be prepared to give it to you with examples on Thursday, just ask on Slack. And we can go back and do that lecture. Or a week. Would you be prepared to do that right now? 5 different ways to explain this formula? Okay, 2. At least 1. Maybe, okay. So, it is always a good question. Do you remember where all this stuff comes from? In a higher dimension, this is a determinant and an absolute value of that. And I could give you a geometric intuition for it, but I can also derive it for you and tell you where that actual absolute value sign is coming from. I will point out, this is identical to what you learned in your first couple weeks of your first calculus class. So when you do transformation of variables, U substitution is the variable we focused on. I don't know if they call it U sub somewhere else, but you could call it whatever variable substitution. That substitution technique is this in disguise. And if you go through that sort of thing where you build up that new integral and take a derivative to get the density, you'll always wind up with this formula. The absolute value sign doesn't pop up there. You just always get positive quantities in the right place. And it's really the chain rule. So if you know what the chain rule is, you know. And that's the way Dylan would talk class, right? Big stuff for you guys to think about. I want to just point out that this prior right here, these priors that we just jotted down, we haven't derived them. We don't have any real intuition for them yet, other than they seem to be good ideas. I want to show you that these 2 priors are the exact same thing. So these have the same input. This is the same info, and what that means is they're transform invariant. So I understand a lot of you just want me to do the conjugate analysis. I'm really just saying things I'm going to see in the next lecture. And I'm going to motivate it and go a little bit deeper. So this is my last aside before we jump into the conjugate analysis. So if I look at this, so I'll just say pi v. Put a little v there, just to remind ourselves, so if we're thinking about our formula, we can think about our formula. I'm going to say this is 1 over v, and what I really mean by that, because it's improper, is I mean this is proportional to 1 over v. You can never normalize it, and from our old analysis using the flat prior, the answer is good. So any way you want to explain that prior, the answer is really a great answer, and it's optimal in all kinds of senses. We'll go into that later, but if we build intervals using that distribution, we'd be optimal in every sense you could like. And our classicist friend would build the same exact interval too. And so everybody should be like it. Unfortunately, that doesn't happen. But let's just show that there's perfect harmony between these 2 statements. So pi v is that, and now I just want to change things around. So v is equal, square root of v is equal to sigma. So that's how I'm thinking about this. So this is my function of v. So this is gv. And that's my specific function. And I need to verify whether or not this is 1-to-1. And in general, it's not. But since we're positive, and variances and sigmas are always positive, on the positive side of everything, it's a 1-to-1 function. So the parabola looks like this. You tell me what the coordinate is here, and I'll tell you. So it's just straight through the function. So now I want to figure out what this is. And I just go to my formula and I do that. So I say proportional to, I got this function right here. What I'm going to look for is everywhere I see a v in here, I'm going to substitute it with its new name for sigma. So this also means that v squared is equal to sigma squared. Or sorry, I got it. Sigma squared is equal to v. So I know every time see a v, I can replace it with a sigma squared. So that's this part of everything. Now I need the derivative part. 1 over d sigma. So this thing right here, we need to play around with. So, and keep in mind what you're calling an operator and how you're using this squared sign in all of this. So this part deserves an absolute value sign. So this part always confuses me when I see squares and I'm thinking about operators, or is that a variable? So let's just go back, and v is sigma squared right here, and sigma is equal to square root of v right here. I need this to be a function of sigma right here. And so this is sigma squared, and you can take that derivative. I'm going to ask you to work through this, and I'm going to give you a quiz on this probably on Friday. Make sure you can transform a random variable. You come up with this. This is 1 over sigma, and there's some cancellation. So make sure you can do that last step. We're going to do another one, and there's another one on your homework where I'm asking you to change log odds. And you don't even have to think of that as a Bayesian calculation. You can just think of it as a transform question. So that's how you transform everything. We're going to do that again. We're going to do it a few times. But if I take one distribution and I transform it, and it's 1 to 1, the distributions are equivalent to each other. So let me just ask you this. So just one more time. So one more aside. We're going to repeat this lecture when we get to Jeffrey's priors, and we're going to drill down this point. So pi mu, proportional to 1. Who thinks this prior makes sense? And would be willing to use this prior analysis on mu? If I tell you it's okay to do it, would you be willing to? I think it's following, yeah. I mean, what else would you do? I think it's a totally reasonable prior on mu in a normal distribution. So let me just think about maybe, I'm going to think about mu just being positive, just to muck around with things. And I don't want to do so I'm only considering a half normal if I did this. Let's say I came up with log of mu, and I called this lambda. So instead of thinking about mu's, I like thinking of log mu's. So that means that mu is equal to E lambda. This is very similar to your other problem. So that's a 1 to 1. I'd be careful on the range that I was on. This is okay. And so I want to build up my prior distribution on lambda right here. So I know this function's not that function. They're different functions describing different random variables. And sometimes I'll just tell you that. They're not the same pi functions. So what does this one look like? Anywhere I see a mu in here, I replace it with my new name for mu. I don't see a mu in there, so this is still proportional to 1. That function doesn't change. Anywhere I saw a mu in there, I replaced it with E lambda, and then I just, whatever this function is, lambda. And this couldn't be any easier. E lambda. So that's my new distribution. I'm going to ask this same question again. Who thinks, for a normal example, or that's a location parameter in a normal example, who thinks that prior makes sense and would use it? Indulge me. Sure. I feel strongly I would choose this one. I wouldn't use anything else unless you told me some special stuff. So who feels like I do? Sure. Okay. Here's the part I really want to know, and I feel like I'm not going to be lucky. We're going to actually take a poll eventually on this, so I want to see hands when we do this for real. But who would use this one? If somebody said, hey, I don't like thinking about Mu, I like thinking about lambda, which is log mu. Who would use this prior? Dylan? No. Okay, are you being facetious? Okay, I appreciate that. I want you guys to just think about this. This has exactly the same information as that one. They're identical to each other. They're just written down differently. So they're one-to-one transformations. No information is lost or gained by moving through this lens. So it's just a different way of thinking about the same thing. So we're going to reconfront that, but I want you to just think about that some more, that this feels good. That's the same thing, but it looks a little bit funky. It looks like this isn't flat right here. So we're supplying information about mu on this scale. It's hardly flat. So we're supplying information in some dimensionality that's not this flat sort of thing that feels like it's informationless, but it has no information about the location of the distribution. We're going to strive for the same sort of thing with our scale analysis. Let's jump over to it. I think this is all going to help us in the future because this is slightly confusing. And you have to see it once or twice. Okay, xi's, normally distributed, mean mu, variance sigma squared. Remind us that I like thinking about this other thing. So that means that the likelihood function for phi, and I'm going to lock down mu, so mu is just a constant, and I'm going to write it out like this. And this looks like this. I goes from 1 to n, 1, I'm going to say 1 over sigma, and I'm going to write it like that, sigma squared. In there, e to the minus 1/2 xi's minus mu squared over sigma squared. And Michael reminded us last time what a gamma looks like. So let me write that down real quickly. A gamma distribution. I'm going to say the random variable is z. And it has two underlying parameters. And if you use this in a Bayesian sense as a prior, we would call those hyperparameters. So just change the language just a little bit. And it looks like this. The bulk of it, the most important stuff, looks like z to the alpha minus 1, e to the minus beta z. And so that's the chunk that's important. And there's some normalizing constant in there. And it looks like this. It's beta to the alpha, so this number to that number, divided by the gamma function of alpha. And I'm going to tell you a little bit about what the gamma function is, and if you can't remember, if alpha is an integer that's positive integer, it's alpha minus 1 factorial. Just to give you some comfort with it. There's a relationship between this function and the beta function, which we had previously seen for the beta distribution. I'll give you a few little highlights that won't necessarily help you in this class, but it's good to know. But that's just normalizing constant. What I will tell you up front is this part isn't going to help you in this class. If we were doing analysis on the degrees of freedom in a normal distribution, that part would come into play. But we will remember this right here. And I also want to point out a lot of textbooks have the beta flipped upside down. I want to point out this looks eerily similar. If I'm thinking about the z as a sigma squared, it looks like this function right in here. Very similar. We have to figure out what the exponent is, but the square root sign is like an exponent. But all my sigma squareds are flipped upside down. And that's not what's called a gamma distribution. That's an inverse gamma distribution. So what I'm going to do to correct all of this, I meant to write sigma squared is equal to 1 over. I was really just jumping the gun on this, and I want to replace all of these with my new way of thinking about sigma squared, which is phi. So I'm going to just change that to 1 over phi right there, and I'm going to change that to 1 over phi. And there's nothing more you need to do. So when I want to talk about that, a lot of people are thinking you need a Jacobian. Right now you don't. So if you want to reparameterize a likelihood function, you just do it. So boom. Change the way I feel about those parameters, how I want to write them down. As long as it's still the same mathematical expression, it's the same thing. So if sigma squared was a 5, my phi is a 0.2. So this thing down here is still a 5. So it's the exact same equation. Later on, when we put a measure on everything and we upgrade it to a random variable, that's where the Jacobian comes in. So if you're thinking you need Jacobian, not yet. That would come through the prior, or if I already updated everything to a posterior, that would come in transforming posterior. Likelihoods are the easiest thing to reparameterize. You just do it, it's math-free. So that's what we've done. And this thing looks, this is going to be phi to the 1/2 power over here. So we'll rewrite that down, and it's getting powered up over here. So we're just going to rewrite that likelihood, recognize probably that the conjugate is a gamma distribution. And what we'll see in our first step of the calculation is when I multiply the likelihood into that gamma form, it still looks gamma. What we'll need to do is recognize what the parameters of that gamma are. And it's pretty easy. It's easier to do than in normal. If you use the original form of the likelihood and not the next one. That's it for now, you guys. So we'll come back, pick up with this stuff, and then I think we'll have a pretty good template for what a Bayesian does in terms of constructing posteriors. They think about priors, they think about what's easiest to them first, aka the conjugate thing, and then they start thinking about which parameters, hyperparameters, and why. And I've already told you, I've proven to you, that limit to conjugate priors are oftentimes very good ideas. Same thing will happen here. Cool. That's it for now.